In couple of previous lecture, we discussed the Legendre equation. Legendre equation is a differential equation of this form. So in linear algebra, we discussed that if you have a certain matrices, then we have the eigen vectors. We get corresponding eigenvectors of the given matrix, which are orthogonal orthogonal vectors, right? So now, after studying this Legendre equation, we can observe that if we have a certain differential equation and we have certain numbers, so we call this number to be some number lambda, which changes depending on the different values of p, we are getting corresponding different solutions y. So we have observed that whenever we discuss the Legendre equation and if we solve the Legendre equation, we get the corresponding Legendre equation for the different values of n, and that are nothing but the solutions which are polynomials, and these polynomials are orthogonal. That is what we discussed in the previous lecture, that whenever we solve such a differential equation which depends on some real number lambda, whenever we take different values of lambda, we get its solutions, which are the Legendre polynomials, and these solutions are non-zero solutions, right? So these functions are non-zero functions. In particular, they are non-zero polynomials, and they are orthogonal. So this property we want to discuss for slightly general differential equation, which is known as Sturm-Liouville problems. So we want to discuss today Sturm-Liouville boundary value problems. So these problems are related to the initial value problems. In initial value problem, we consider we fix value of the solution at particular points, right? In the same way, we in this differential equation will have a certain condition along with the differential equation. So therefore, it is known as boundary value problem. So first of all, what are such equations? So consider the differential equation of the form derivative of function px times y dash plus lambda times qx plus rx. Times y is equals to 0. So this differential equation is known as the Sturm-Liouville. This was studied by Sturm and Liouville, and therefore it is known as Sturm-Liouville equation. So if we get non-zero solution yx, so let us call this equation number 1. The yx of the Sturm-Liouville equation 1 for some real number lambda, right? So suppose this differential equation has a non-zero solution yx. So non-zero solution yx means yx is not identically zero function, for some real number lambda, then we say that so this solution y depends on lambda, so we can call it y lambda, right? So y lambda is a non-zero solution of the differential equation corresponding to lambda. Then we say that y lambda is the eigen function, right? Instead of eigenvector, here the solution is satisfying the equation corresponding to value of lambda. We call y lambda is an eigen function corresponding to corresponding eigenvalue lambda. Right. So once again, if we consider the Legendre equation, then we know that for different values of this number lambda, so lambda here is this number, because this differential equation we can write in this form, right? Derivative of some function y dash times lambda y, right? So that is exactly, this equation is an example of Sturm-Liouville problem, and the corresponding non-zero function y for different natural number of p, we are getting different solutions which are the Legendre polynomials. So Legendre polynomials Pn is the eigenfunction corresponding to an eigenvalue n plus 1. So let us take one yes example. So the Legendre equation, that is nothing but derivative of 1 minus x square times y dash, so that is this part, plus n so plus, we can say pp plus 1 or nn plus 1, better to take special value nn plus 1 times y is equals to 0. So here this number is lambda. So either we take lambda y in this equation and then take a special case lambda is equals to nn plus 1. That also we can do. Right. So this is a general Legendre equation where we know that we take in the Legendre equation lambda is equals to p into p plus 1. So the Legendre equation is an example of Sturm-Liouville problem where if we take special value of lambda, that means when we take p is equals to n, so we get lambda n is equals to nn plus 1, right? Some particular value of lambda. Why we are calling lambda n? Because this value depends on n. So here for this particular value of nn plus 1, we get non-zero solution Pn, which is a Legendre polynomial. Right, so that means the Legendre polynomial are eigenfunctions. So which Legendre polynomial? So Legendre polynomial Pn is eigenfunction corresponding to eigenvalue and lambda is equals to nn plus 1. N times n plus 1. Right. So this is an example of eigenvalue and eigenfunction. So the question is that here we know that the eigenfunctions, which are the Legendre polynomials, that we have observed that they are mutually orthogonal. Right. So that means we get this inner product to be 0 whenever m and n are different. So in general, is it possible that if we have a Sturm-Liouville problem, so what can we say about the solutions with non-zero solutions corresponding to different values of lambda? So whether they are mutually orthogonal or not, right? So let us verify that. So suppose we have two solutions, ym and yn, are two non-zero solutions of the Sturm-Liouville problem. That means ym and yn are two eigenfunctions. Just a minute. Two eigenfunctions corresponding to eigenvalues lambda n and lambda m. Right. So this lambda value depending on natural numbers m and n, and they are different real numbers, and corresponding solutions we are getting yn and yn. Right. So this is given for the Sturm-Liouville problem. So that means what? Let us write down the equation. So ym and yn are solution corresponding to lambda n and lambda m. So that means we get the differential equation is to be d by dx times px ym dash, right, plus lambda m times qx plus rx times ym is equals to 0. So just verify that. If we substitute in this equation, instead of y is equals to ym corresponding to lambda m, then we get this equation. So that means ym is a solution corresponding to the value lambda m. Similarly, we get the another solution, another equation, because we also know that yn is a solution corresponding to lambda n. So I think I should write in order. So this should be ym, this should be yn. Right. So ym is a solution corresponding to lambda m. Yn is the solution corresponding to lambda n. So that will give us second equation by substituting yn and lambda n. We get yn dash plus lambda n qx plus rx. Yn is equals to 0. So now we have these two differential equations, and if you recall the orthogonality, what we have done is we had these two equations. To show the orthogonality, we have considered this particular equation where this is lambda n, lambda m, right, and these are nothing but the solutions. So that is yn and ym. Alright, so we'll consider this term, and for that we need to multiply the first equation by ym, the second equation by yn. Right. So similar thing we will do here. So let us call this equation number 1, equation number 2, right? So multiply first equation by yn, and second equation by ym, and subtract these two equations, these two new equations. So if we subtract, then we'll get the corresponding equation to be, yes, let us do that. So first equation, we get yn times d by dx of px ym dash plus yn times lambda m qx plus rx times ym is equals to 0. This first equation, we are subtracting the second equation, that is ym times d by dx of px yn dash, right, plus, so here also this sign will be negative, minus ym times lambda n qx plus rx times yn is equals to 0. Right, so now if we add these two equations, then what we shall get is, we shall get only the second term, because the first term will cancel out because they have different positive and negative sign. That is the same term with different signs, so that will cancel out. What we'll get is yn times pym dash, derivative of that, minus ym p times yn dash, derivative of them, plus lambda m minus lambda n times q times ym into yn, and this equals to 0. Right, that is what we get, difference of this term with this term.
So why these two cancelled?
The first term,
So why
yeah,
cancelled?
the first term will yeah, you're right, so it won't cancel, right? So that is what we have written, the p terms, this one and this one. Yes, so that has not cancelled out, you are correct. So but one term has so yes, you are right, so that is r term is cancelling out. Yeah, so you are correct. Right, so the q term will be here, and as you mentioned correctly, that p term will not cancel out, that is exactly this term, right? Fine. So now what next we will do is, we will take this constant separately, right? So the corresponding term we are getting is lambda m minus lambda n. Let us integrate that. So we will integrate lambda m minus lambda n, integral a to b q times ym into yn dx. So what we have taken here was integration from -1 to 1, right? So that was the given domain of the solution. So in this case, we don't know what is the domain. So what we shall consider is, in the problem, we shall take the arbitrary interval. So this differential equation is given for a less than or equal to x less than or equals to b. So differential equation we want to solve over the closed interval AB. So we want to find the solution y over the closed interval AB. So that is the reason we will define, we will integrate from a to b, right? That is the interval over which we are looking for the solution. And yeah, so this will be equals to, from this equation, this term, the other term will take on the other side, it will be negative. What we shall get is integral a to b ym p times yn dash derivative of that dx minus a to b yn p times derivative of pym dash dx, right? And then we know that in the next term we are using integration by part. So if we use integration by part, so we need to integrate this term and differentiate this term. So that means we will get the first term to be ym times pyn dash, the limit is from a to b, minus the second term of this integral will be a to b ym dash p times yn dash dx, right? So that is the first integral. Now second integral, similarly, if we expand, we get yn pym dash, limit is from a to b plus integral a to b yn dash pym dash dx, right? So now again here we can see that if there is any term cancelling out, so here this term and this term is same with the opposite sign, so that means those terms will cancel out. So the remaining term we need to substitute at the value a and value b. Alright, so these two will cancel out, same term with opposite sign. And the other term, if you substitute x equals to b, we get ym function at b, p function at evaluated at b, yn dash at b, minus the term evaluated at a. We get ym a, p evaluated at a, yn dash at a. Similarly, the second term with the negative sign, so we get yn b, pb, this one with the plus sign. So that is yn a, pa, and ym dash a, right? So just we have write down the terms in terms of a and b. And what are a and b? A and b are the endpoints of the interval on which we are looking for the solution. So now from these terms we can see that the first term and the third term involves pb, and these two terms involve pa. So let us separate these terms. So the coefficient of pb will be ymb, yn dash b minus ynb, ym dash b, right? And the last term will be minus pa times, so ym a, yn dash a minus these terms, that is yn a, ym dash a, right? So we have separated the term multiplied to pb and pa, and these terms we already know what is that. That is nothing but the Wronskian, right? So that is equals to pb, we can call this Wronskian evaluated at b, minus pa times Wronskian evaluated at a, where what is the Wronskian here? Wronskian here is wx is determinant given at the solution. Yeah, so that is in terms of ym and yn function. So first row will be ym evaluated at x, yn evaluated at x. Second term is its derivative, right? That is how we define the Wronskian. So whenever we substitute x equals to b, that is wb, is exactly this term, right? This bracket. And whenever we substitute x equals to a, it is exactly this term, the Wronskian at a. And what is ym and yn? Ym and yn are the non-zero solutions of the Sturm-Liouville problem, corresponding to the numbers lambda m and lambda n. Yeah, so if we go back again, then we know that here we got the solution to be 0, right? And that has given us the orthogonality of the Legendre polynomials. But here, if you see, we are getting this integral to be, we want to show this ym and yn are orthogonal up to this function q, right? But here the integral turns out to be this particular number. So that means the orthogonality depends on these values, right? Basically on the Wronskian evaluated at the endpoint of the interval, as well as the value of the function p at a and b, right? So here it was 0 because yeah, so here we are not getting. So that means what? So we need to take some assumptions. So if pb wb minus pa wa is 0, then we get the integral to be 0, right? So integral of ym yn up to this function q dx is equals to 0, and hence we get orthogonality of ym and yn function, right? And what are the ym and yn? Ym and yn are the eigenfunctions. Yeah, so everything boiled down to this particular condition, and this particular solution term is 0 if we take one of this number is 0 as well as one of this number to be 0, right? Then the multiplication will be 0. So this term will be 0 if we condition some special condition. So for example, if we take special condition like ya is equals to 0 and yb is equals to 0. So what does this mean? This means we are given this Sturm-Liouville equation, that is equation number 1, along with we are posing the condition on the solution y, that is we are looking for the solution which satisfies this condition that every solution should be 0 at the endpoints, right? So if we take this condition, then what we get all the solutions satisfying this condition. That means ym of a is 0, yn of a is 0, as well as they satisfy this condition also. That means each solution value of at b should also be 0, right? So if this condition is like initial condition, which we consider in the initial value problem. So similar condition, but not in that form. So for the second order differential equation, we consider initial condition like y of x naught is y naught and y dash of x naught is y1, right? Something like this. We consider this condition in the initial value problem, but here the condition is slightly different. That we are considering is y0 at the end point of the interval, and endpoints are basically known as uh, boundary points, right? So therefore, such a condition is known as boundary condition. Is known as boundary condition. So if you take boundary condition, this particular condition, then we get this 4 value to be 0, and whenever this 4 value is 0, we can see what is the effect on the corresponding Wronskian. So if we take this this ym is 0 and yn is 0, then these values will be 0 in WA, right? So that means one of the row is 0, so the Wronskian itself is 0, right? So WA will be 0. Similarly, the second two condition, if we take, then in the computation of WB, we get YMB and YNB, and that is 0. So that means first row of WB is 0. So therefore, WB itself is 0, right? So that means WA and WB is 0. So this term will be 0, right? And in that case, we get orthogonality. So therefore, WA is 0 and WB is 0, and we get orthogonality. Similarly, if we take another boundary condition, which is in terms of derivative. So suppose we take y dash of a is 0 and y dash of b is 0, right? So you must have guessed that this is basically the second row of the Wronskian, right? So what is the second row of the Wronskian? That is in terms of the derivative. So whenever we take this second boundary condition, again we get yn dash and ym dash is 0 at the end point. Right, and again we get WA is 0 and WB is 0. So therefore again we get a ym and yn orthogonal. Right. So let us go back to again the the example of Legendre equation. Yeah. So while Legendre equation is a special case of Sturm-Liouville problem, so we know lambda is this, right? If you compare it with this equation, lambda is that. Why? Because the last term is, just a minute. If we compare these two equations, the Legendre equation with the Sturm-Liouville problem, then we can observe that we need to take R to be 0, right? Q to be 1. So then the last term will be essentially this term. And the first term, if we compare with the Sturm-Liouville problem, we essentially get Px is 1 minus x square, right? So if we take Px is 1 minus x square, then now we can see that from this computation, if we take px is 1 minus x square, and we take the interval of Legendre equation, which is -1 to 1, then for 1 minus x square function at 1 and -1, we get pb and pa is 0, right? So that means for that Legendre equation, we don't need any boundary condition because the p itself becomes 0, right? So therefore we have not taken any condition here with the Legendre equation, but when we generalize it, we need such a condition. Okay, so let us take one example in which we take some simple example, not like uh, a difficult one. So for simple Sturm-Liouville problems, how to find the eigenfunction? So that is a question. So one first example is for lambda is equals for any real number lambda, consider the Sturm-Liouville problem. So we shall shortly call it SLP, that is y double dash plus lambda y is equals to 0, right? And we are taking the boundary condition to be y dash of 0 is equals to y dash at pi is equals to 0, right? So basically these are endpoints. So that means we are taking the value of x between 0 and pi here. Yeah, so what is the question? Question is find all possible eigen functions. So when we have such a, so is it clear this is a Sturm-Liouville problem, right? So if we go compare it with the standard equation, yeah. So basically p is 1, so we get y double dash term plus lambda. So r is 0 we can take, and q is 1 we can take. So that means we get this equation as a special case of Sturm-Liouville problem. Yeah, and to find the eigen function, we need to take different values of lambda, and we need to check whether corresponding to that eigenvalue there is any eigenvector or not. So similar to the matrix case. So since lambda is a real number, there are three cases: either lambda is 0, lambda is positive, and lambda is negative. So start with case 1, that is lambda is 0. So if lambda is 0, if we substitute it in the equation, we get the corresponding equation is y double dash is 0. So that means we get y dash to be the number, let us say some number beta, right? If we integrate both the side, and similarly again if we integrate, we get this to be alpha plus beta x, right? So we get the solution corresponding to lambda 0. The general solution is this one, but we are looking for the solution which satisfies the boundary condition, right? So boundary conditions are in terms of the derivative is beta. So if we uh, so y dash at 0 is 0, and what is y dash at 0? Y dash is beta everywhere. For all values of x, y dash is beta. So that will give us beta is 0, right? Using the first boundary condition, y dash 0 is 0, we are getting beta is 0. If we use the second condition, again we'll get beta is 0. So that means the solution is yx is equals to alpha, right? And so if you take alpha is non-zero, the corresponding is a solution. Yeah, so for corresponding to eigenvalue, we are looking for non-zero solution, right? So depending on alpha is 0 or not, we will get the non-zero value of y. So for example, or in particular, yx is equals to 1 function, which is taking value 1 everywhere, is an eigen function corresponding to lambda is equals to 0, right? We cannot take alpha 0 because that will become 0 function and eigenvector cannot be 0. Now in case 2, we will take value of lambda to be negative, right? So in this case, so for negative value of lambda, is there any non-zero solution of the given differential equation, right? So if lambda is negative, so so that means minus lambda is positive, right? So lambda is positive means minus lambda we can write as a some number square, right? If you have a positive number, it is always a square of some number. So that number we are calling mu. So basically mu is the square root of minus lambda. So in this case, what is the solution? Therefore, the given differential equation is y double dash plus lambda y is 0. And if we substitute lambda equal to minus mu square, we get this equation, right? Now you can understand why we have taken lambda equals to minus mu square, because we get the differential equation of this form, which is a differential equation, second order differential equation with the constant coefficients. So that means we can find the corresponding characteristic equation, that is minus m square minus mu square is equals to 0, and that will give us two different values of m, that is m is equals to mu and m is equals to minus mu, right? And since lambda is negative, mu and minus mu cannot be same, they are different numbers. In this case, we know the general solution is c1 y1x is e power m1x. So this is our m1, this is our m2. So that will give us c1 e power mu x plus c2 e power minus mu x. Just by substituting these values, we get this general solution. Now from this general solution, we need to find the solution which satisfies the boundary conditions, and the boundary condition is in terms of the derivative. So let us find out the derivative of this function. So that will give us the derivative is c1 mu times e power mu x minus c2 mu times e power minus mu x, right? So just check if I do any mistake, just let me know. Okay, so this is our y dash, and the initial condition is y dash at 0 is 0 and y dash at pi is 0. So y dash at 0 is 0 gives us, if you substitute x is 0 in this, we get c1 mu, right, minus c2 mu, and mu is non-zero, so that will give us, this term is 0 and mu is non-zero, so mu we can take common and cancel out both the sides. We get c1 minus c2 is 0. right? And then we get C1 is equals to C2. So that is the first condition we are getting from the first boundary condition. And using the second boundary condition, that is y dash pi is 0. So again we substitute x equals to pi, we get C1 mu e power mu pi minus C2 mu e power minus mu pi. Right, and then we substitute this condition here. So because our all the solutions should satisfy both the conditions, so we substitute C1 is equals to C2 here, we get C2 mu e power mu pi minus C2 mu e power minus mu pi is equals to 0, right? So what you are using, because C1 is equals to C2. Yes. So now we can see that this is nothing but C2 times some fixed number, because mu is fixed and pi is fixed, and that number is non-zero number, so that we can cancel out both the side. So we get C2 is equals to 0, right? Why? Because mu e power mu pi minus this number is a non-zero number. Mu is fixed, mu is some real number. So what did we got? We got, in this case, we got the solution which satisfies C1, C2 are same and C2 is 0. So that means, what is the solution? If we substitute C1, C2, 0 in this general equation, we get the only one possible solution, that is yx equals to 0, right? So therefore we get only one solution, yx equals to 0 in this case. And we know that yx is equals to 0 is not an eigenvector, because it is a 0 vector. So that means no eigenvectors, no eigenfunctions corresponding to lambda less than 0, right? So if lambda is less than 0, there is no eigenfunction. Lambda is equals to 0, we have got one eigenfunction. And the third case is remaining for lambda positive. So that maybe you can try yourself. We will complete that part tomorrow.